Okay, so we've come to the last lecture of the course, and it's a review for the last exam. It's covering chapters 28, 29, and 30 in the Giancoli book. And so it's focusing on magnetism. And so the first chapter that we're covering is chapter 28, which is sources of the magnetic field. And the root of chapter 28 is the Biot-Savart law. This is a vector integral equation. So it's a little bit more complicated than some of the other equations we've looked at. But we'll talk about each of the parts of it in turn. So there's a universal constant mu naught times the current I divided by 4 pi times the integral of the cross product of dl and r, or dl and r hat, divided by r squared. Or you can write that as the cross product of dl and r divided by r cubed. Usually when you're setting up the integral, the latter is the better way of writing it. So mu naught is called the permeability of free space. It's a universal constant. Its value is 4 pi times 10 to the negative 7 Tesla meters per ampere. And if that looks like an arbitrary number, it's because it is. And we'll see why at the end of this chapter. So I is simply the current. dl is a vector corresponding to the infinitesimal length of wire. So it needs a magnitude and it needs a direction. R with the arrow is a vector pointing from the infinitesimal length of wire to the point where B is being evaluated. R without a hat or an arrow is simply the magnitude of R arrow, of that vector. And then R hat is a unit vector pointing in that direction. So it's equal to R arrow divided by the magnitude R, so that its own magnitude is simply 1 and dimensionless. So the first example we looked at was a long straight wire. And so qualitatively, there were a couple of important things you could figure out before you got to the math. The first is that if you draw a circle around the wire, so the plane of the circle is perpendicular to the wire. And every point on that circle would have the same magnetic field, that it varies with distance and it doesn't have an angular dependence with it. And that's going to come into play even more when we talk about Ampere's law in a couple of minutes. The second thing is that if you take point P along the circle, as you move point P around the circle, the magnetic field points around, circles the, goes around in the circle. So that B makes circles around the wire, and that the magnitude of B varies with distance, but is constant for the same distance, capital R, around the wire. So then we got into the qualitative part, or quantitative parts of this. So dl, so we define the x direction as the direction of the wire. It's a straight wire, so that's simple enough. dl is just dx I hat. And then you need r, the distance from an infinitesimal length of wire to the point P where you're evaluating the field. So you put the point P on the y-axis. And so it has a distance, capital R, above the wire, or perpendicular distance, capital R, above the wire. So the y component of R is going to be capital R. So you can have a plus capital R j hat. And then the other thing to keep in mind is that when the x coordinate is to the left of the wire, the R vector points to the right, of the origin rather, and when the x coordinate is to the right of the origin, the R vector points to the left. So the directions are reversed. And so that the x component of the R vector is simply negative x I hat. So that R is negative x I hat plus y j hat. So then you do the cross product, and then you do the integration, and you get the magnetic field is equal to mu naught I over 2 pi capital R. That's the magnitude. And the direction is in the positive z direction, so it's k hat. And so if you define the positive y direction as from the wire to the point where you're evaluating the field perpendicularly, and then so you define x as the direction of the current, y is the direction from the wire to the point where the field is evaluated, then the positive z direction is the direction of the magnetic field. So if you move point P in a circle around the wire, the magnetic field will curl perpendicularly to V, so it'll follow the arc of the circle. That brings us to the second application we did, and that's with a loop of wire. So it's a single loop, and you're looking on the axis of that wire, and so a distance z away from the plane of the loop. So a perpendicular distance z away. The radius, again, is capital R. So the plane of the circle is in the xy plane. So dl has x components and y components. And R has an x component, a y component, and a z component. So it's a little bit more complicated. But you can figure out how the x components of dl, x and y components of dl work. The x component is related to the sine of theta. It's 0 when theta is 0. So defining the x-axis as theta equals 0. When theta equals 0, there is dl points in the positive y direction. So the y direction is proportional to the cosine of theta, because remember, at the 0 degrees, the cosine of theta is 1. The x component is proportional to the negative of sine of theta, because when it's at the top of the trajectory, it's pointing left. So when theta is +1, you're pointing left. When the sine of theta is -1 at negative 90 degrees or negative pi over 2, the dl vector is pointing to the right, and if we're making a counterclockwise circle. And so the x component then is proportional to the negative of the sine of theta. So, but you multiply both those terms by the magnitude of dl, and the magnitude of dl is just the arc length, which is capital R d theta. So it's capital R d theta multiplied by negative sine theta I hat plus cosine theta j hat. And so that's dl, and it takes a little bit of thinking to come to that. I don't know if you've done anything in polar coordinates, but that's basically how you need to do this. You need to express x and y in terms of r and theta. And then you need to do the same thing for the r vector. This is a little bit simpler because, if you're given a point on a circle and you want its position vector, when that position vector points from the origin to the point on the circle, well, that's equal to r cosine theta I hat plus r sine theta j hat. However, the r vector in this case is pointing from the circle to its center and then out in the z direction. So we're breaking it into components. So it becomes negative capital R cosine theta I hat minus capital R sine theta j hat plus z k hat. And so that's the r vector. And so you have dl and you have the r vector. You take the cross products of them and you get components in 3 dimensions. But we can do something quantitative that we can eventually verify using calculus. If you take a point along the circle or along dl, curl it back towards the center, or curl it back towards the point where you're evaluating the field, you see your thumb points up and also out of the circle. But when you integrate over the full circle, you see the x and the y components cancel out, but the z components add together. And so when you do that integral after evaluating the cross product, you integrate from theta from 0 to 2 pi. You see the x and the y components do in fact cancel out, but you still have a z component. And that enables you to solve this integral. So it's in the z direction, it's along the axis, and that brings us to another important right-hand rule, which is number 4, our fourth right-hand rule. You curl your fingers in the direction of the current, your finger points in the direction of the magnetic field. So, and note the similarity with the magnetic dipole moment. It's basically the same thing. So what that's telling you is that a loop of current creates a magnetic field that points in the same direction as its dipole moment. And we also learned in the last chapter that when iron, which has a lot of rotating electrons with their own dipole moments, that absent an external magnetic field, they're rotating in random directions so that the net magnetic field is 0. But you expose it to an external magnetic field, the potential energy is minimized when the dipole moments line up with the magnetic field. But that also means that the potential energy is minimized when the magnetic fields created by those moving electrons line up with the external magnetic field. So what you wind up doing is significantly magnifying whatever external magnetic field exists simply by putting iron inside it, for example. And the other consequence of this is that the magnetic field of a refrigerator in the vicinity of a refrigerator magnet will line up with the magnet so that its south pole faces the magnet's north pole, or vice versa, and you get attraction. And so that's what keeps the refrigerator magnet in place. So there are a couple of things that come as a direct result of this. That brings us to Ampere's law. Much like Gauss's law is a direct consequence of Coulomb's law, Ampere's law is a direct consequence of the Biot-Savart law, but it can be used to make complicated integral problems, or turn complicated integral problems into simple algebra problems. The most obvious example being the long straight wire that we've talked about. So the basic presentation of Ampere's law is that the closed path integral. So remember, Gauss's law involved a closed surface. Ampere's law involves a closed path. So you're taking the dot product of B and DL across a closed path, and that's equal to mu naught times I, which is the current that crosses through that, the plane of that closed path. So the most obvious example is a long straight wire. So we already figured out qualitatively that if you're a distance r away from a long straight wire, a perpendicular distance r away from that wire, the magnitude of B is going to be constant. So we figured that out before doing any of the math. And we also figured out before doing any of the math that B was going to make a circle around the wire. And so the dot product of B dot DL in this case, because the magnitude of B is constant along that path, and B is always pointing in the same direction as DL, it's going in the circle, and you make DL a circular path. So that dot product, or the integral of that dot product, is simply the constant magnetic field B multiplied by 2 pi r, the circumference of the circle. So you solve that for B, and you get mu naught I over 2 pi r. So it takes you 2 steps to solve the magnitude of B, whereas doing it via the integral took way more than 2 steps to solve. And so, again, much like Gauss's law, Ampere's law can take complicated integral problems and make them relatively simple. And from there, we talked about 2 parallel conductors, or 2 current-carrying wires, I1 and I2, separated by a distance d. And we were asked to figure out the force per unit length on those wires. So remember, currents create magnetic fields. Magnetic fields exert forces on currents. So the current due to one is going to create a magnetic field that exerts a force on the other. And from Newton's third law, before we even get into any math, you understand that they exert equal and opposite forces on each other. And so we went through the derivation. And so what we found out is the force per unit length that the two wires exert on each other is mu naught times I1 times I2 over 2 pi d, where d is the distance between the two wires. And if the currents are going in the same direction, the wires will attract each other. And if the currents are going in opposite directions, the wires will repel each other. And that brings us to the official definition of the ampere. So we've kind of been hinting at this through most of the course up to this point. But if two long parallel wires a meter apart carry the same current, and the magnetic force per unit length on each of the wires is 2 times 10 to the negative 7 newtons per meter, then the current is defined to be 1 ampere. So that's how you define the ampere, and that's how you get mu naught and epsilon naught and the coulomb and the ohm and the volt and the farad and the Tesla. They all derive from this definition of the ampere. But keep in mind that there are some electrical and magnetic values that don't actually depend on how you define the ampere. So the time constant, R times C or R times L, that we'll talk about in a couple of minutes, are examples of values that don't depend on the definition of the ampere. Their units will always be in seconds. Another example, and this is a very, very important example that you get to in chapter 21, which would be in physics 3. The product of mu naught and epsilon naught, the two fundamental constants, does not depend on the value of the ampere. It does depend on the value of another fundamental constant of the universe, but we'll leave that to physics 3 for you to figure out. And the last thing we're going to talk about in this chapter is the solenoid. The solenoid is a tightly wound coil of wire with capital N turns and a length L. So think a cylinder with capital N turns and a length L, or small n turns per unit length. You can write it either way. And so the magnetic field, and you can figure this out from Ampere's law, the magnetic field is equal to inside the solenoid and not too close to the edges, is equal to mu naught times capital N over L times I, or mu naught times small n times I. And so that's the magnetic field inside the solenoid. It is uniform. So much like the infinite sheet of charge allows you to create a uniform electric field or a functionally uniform electric field, the solenoid allows you to create a functionally uniform magnetic field. And you use the same right-hand rule to determine the direction that you used for figuring out the magnetic field due to a single loop of current. And that's that you curl your fingers in the direction of the current, your thumb will point in the direction of the magnetic field. And the other example we talked about is the toroid. And that's a circular solenoid of radius r. You can think of it as a donut. So you have empty space in the middle. And the magnetic field in the solenoid, or in the toroid rather, if you're a distance r away from the center of curvature, is equal to mu naught times capital N times I divided by 2 pi r. So the magnetic field inside a toroid, where you've got turns of wire wrapped around a donut-shaped coil as opposed to a cylindrical shaped coil, it's not uniform. But if the width of the toroid is small compared to the distance r from the center of curvature, then it's functionally uniform. And so when you think of the really large particle accelerators, those are toroids with really, really large values of r and comparatively small widths, so that the magnetic field is approximately uniform inside the coils. So that is chapter 28. Now we're going to move on from chapter 28 to chapter 29, which is about Faraday's law of induction. And before you can get to chapter 29, before you can get to Faraday's law, you need to introduce what's called the magnetic flux. And the magnetic flux is very similar to the electric flux. It's a measure of the component in the magnetic field that crosses through a surface multiplied by the area of that surface. And The generalized form, in case either the magnetic field is not uniform or the surface is not flat, is that the magnetic flux is the integral of the dot product of B and dA. And remember, the vector dA points perpendicularly to the surface. So it's not the angle that the magnetic field makes with the plane of the surface, but with a line perpendicular to the surface. And if B is uniform and the surface is flat, then the magnetic flux can be written as B times A times the cosine of theta. And again, theta is the angle the magnetic field vector makes with a line perpendicular to the plane of the surface. The unit of magnetic flux is the Weber. So magnetic flux, unlike electric flux, has its own SI unit. The magnetic equivalent of Gauss's law, so if you integrate the magnetic field or the magnetic flux over a fully enclosed surface, you're always going to get zero. And you're always going to get zero because you can't have a magnetic north without a magnetic south pole. With electricity, with Gauss's law, you can have isolated positive and isolated negative charges. And so you can have a value, a non-zero value for the electric flux over a fully enclosed surface. But with magnetic flux, you can't have magnetic north without magnetic south. So regardless of the shape or size of the fully enclosed surface, the magnetic field is going to go out for part of the surface and it's going to go into other parts of the surface. And integrating over the full surface, you're always going to get zero. And that's when we talk about Maxwell's equations in chapter 31, that relationship is going to be important. And that brings us to Faraday's law of induction. Faraday observed that when you change the magnetic flux in any way, so again, going back to the equation, the simplified version of the equation, it's equal to B times A times the cosine of theta. So if you change the magnetic field, you change the shape of the loop, or the surface enclosed by a loop of wire, or you change the angle that that surface makes with the magnetic field. So if you change B, you change A, or you change theta, you're changing the magnetic flux, and any of those changes will cause an induced voltage within the loop. And that voltage, or the magnitude of that voltage, is equal to the number of turns of wire in the coil, or the number of loops of wire in the coil, multiplied by the rate of change of the magnetic flux. So the more quickly the magnetic flux is changing, the greater the induced voltage. And so those were working with the magnitude. With direction, you need to include a negative sign. And what the negative sign means is that the induced voltage will oppose whatever change in the magnetic flux caused it. So let's let the loop lie in the XY plane. If the magnetic flux is increasing, the induced current will create a magnetic field that points opposite to the Z component of the original magnetic field. If the magnitude of the magnetic flux is decreasing, the induced current will create a magnetic field that points in the same direction as the Z component of the original magnetic field. So again, you think a coil of wire, if it's in the XY plane, the current or the magnetic field due to the current in that wire is going to point in either the positive Z direction or the negative Z direction. And so this is how it depends. So if the magnitude of the magnetic flux is increasing, then the induced current will create a magnetic field that points in the opposite direction of the Z component of the initial magnetic field. And if the magnetic flux is decreasing, or the magnitude is decreasing, the magnetic field, or the induced current's magnetic field, will point in the same direction as the Z component of the original magnetic field. And so the right-hand rule, it's basically the reverse of right-hand rule number 4. Instead of curling your fingers in the direction of the current and pointing your thumb in the direction of the magnetic field, you're first pointing your thumb in the direction of the magnetic field caused by the induced current, and then curling your fingers in the direction of the induced current. And that's how you figure out what direction the current is pointing. So there are a couple of steps involved in that. We went through a couple of examples that illustrated that. And that brings us to motional EMF. So if you have an object or a conducting object moving in a magnetic field, the electrons will be forced to one end of the conductor. So that conductor will have a negative side, and the side where the electrons have left, where there's a shortage of electrons, that's going to have a positive side. So you're effectively creating a positive terminal and a negative terminal with a potential difference between them. And but as the positive and negative terminals build, as the charge accumulates on one side, so you have electrons accumulating on the negative side, and then you have a positive net positive charge on the other side, you're also creating an electric field whose force is going to be in the opposite direction to the magnetic field. And so what happens is the charge builds up until the electrical force is equal and opposite to the magnetic force. And that happens when E is equal to negative V cross B. And so figuring out the potential difference from that, you have delta V is equal to negative E dot dl. So the negatives cancel out, and you get delta V is equal to, and that's delta capital V, the capital V being voltage, is equal to the integral of the cross product of small v and b, velocity in the magnetic field, dot dl, where dl is the length of the conductor. In the special case where the velocity and the magnetic field are constant and perpendicular to the conductor, delta V is equal to, or delta capital V is equal to B times L times small v. So there are a couple of ways to write that. There's a general way, and then there's the specific way that you can use with simplified cases. But there are some times where you're going to need the general case. I think I forget whether it's a recitation or a homework problem that you're going to need, or that you needed the general case. So that brings us to an AC generator. So you have a conducting loop. We'll make the conducting loop rectangular, although the final equation applies universally. But we'll make it rectangular for simplicity. So you have some form of energy, whether it's the wind, heat from burning gas or coal, heat from splitting an atom, something supplying energy that turns the loop of wire, the coil of wire, with an angular speed omega. And so what happens is you have, in this case, we have a rectangular coil. The length is L and the width is A. And so the axis of rotation is on the side that's a length A. So that's the wires where the motional EMF is going, the portion of the wires where the motional EMF is happening are a distance A over 2 away from the axis of rotation. So the magnitude of small v cross b is v times the sine of theta. And again, theta is the angle that v makes with b. But remember, the loop is rotating. So you can think of theta as being omega times t. And so the EMF is equal to 2. It's equal to 2 because you've got a motional EMF on two sides, both sides of length L. So it's equal to B times L times V sine theta, and then multiplied by 2 from that. But you can also write V, the linear speed, as being equal to the axis of rotation times omega. So you can write V as being equal to A over 2 times omega. So you can write that as, so you have the 2 and the over 2 canceling out. So you can write that as B L small a omega times the sine of theta. And so, again, the 2's cancel out, and L times small a is just the area of the loop. And again, that applies universally. It doesn't actually matter what the shape of the coil is. And so what you get is, for one loop, the EMF induced is equal to B, the magnetic field, times A, the area enclosed by the loop, times omega, the speed at which it's rotating, times the sine of omega t. And if you have capital N total loops, the EMF is equal to NBA omega times the sine of omega t. So if you're devising a generator, you want to figure out what value of N, and keep in mind that the greater the value of N, the harder it is to turn the loop, so the smaller the value of omega. So you want to find, you want to figure out what value of N optimizes that product, N times omega. And NA times omega, the greater the value of A, the harder it is to turn the wire. So you want to find the value of N that optimizes that combination. But EMF is equal to N times B times A times omega, think National Basketball Association, times the sine of omega t. And you can also derive the same relationship using Faraday's law. So going back to delta V is equal to negative N times the derivative of the magnetic flux, you'll get the same exact result from that. And so AC is the root of our modern electrical grid. Nearly every form of power generation, with the exception of solar, generates an AC current. And with solar, you have a device called an inverter that takes the DC input and puts it into an AC output that's compatible with the grid. But our grid runs on AC, and the reason it runs on AC is because of an invention of Nikola Tesla, whose the magnetic field unit is named for. I call the transformer. So if you look at the power lines outside your house and you see a bucket, that bucket is the transformer. And so what transformers do is they take an input voltage and current combination and convert it into an output voltage and current and combination that's more suitable to what you need. So how does that work? So at the power supply, you're getting a certain voltage and current out from the power source. So it goes to a transformer, and usually in this point, it's a step-up transformer, meaning the voltage increases. So how does that work? So you wrap a certain number of turns, you have a coil with a certain number of turns for the input wire, which is equal to, so with N1 turns. And then on the other side of an iron core, you have a coil with a certain number of turns wrapped around it called N2. And so because it's iron, the alternating current coming from the input coil is creating an alternating magnetic field and an alternating magnetic flux, which is inducing an alternating current in the output coil of wire. But the magnetic flux between the wires is between both coils is the same. So what that means is that the ratio of the output voltage to the input voltage, delta V2 over delta V1, is equal to the ratio of the turns in the coil. So delta V2 over delta V1 is equal to N2 over N1. So with a step-up transformer, the output coil has more turns than the input coil and the voltage increases. With a step-down transformer, the output coil has fewer turns than the input coil and the voltage decreases. So what does that have to do with current? Well, power is very nearly conserved. You lose a little bit of energy in the iron core, but not that much. So the product of current and voltage is constant. So if you double the voltage, you're reducing the current by half. Why does that matter? Well, if you're transporting current over a long distance of wire, you have what's called line loss. So some of the power is getting lost to the resistance in that wire. Now, a copper wire, a short length of copper wire has a negligible amount of resistance. But if you're talking about a few hundred miles of copper wire, the resistance adds up to something noticeable, and then the energy that's taken out of this wire adds up to something noticeable. So line loss is equal to I squared times R. And you want to minimize that value for, if setting up a transformer going to a long distance wire. You want to minimize the current going across that wire to minimize the amount of power that's lost in the wire. So at the power station, you have a step-up transformer converting the input to high voltage, low current. That gets delivered along the long-distance lines, and so those are high voltage. Those are dangerous to touch. When you get towards the home or the business or whatever location you're going to use the electricity, you have a step-down transformer converting it to a relatively low voltage and a relatively high current that can get delivered into the house. And then maybe in your appliance, you'll have an additional transformer converting the input voltage and current into a combination that's more suitable for what you need for the appliance. So that's chapter 29. And then that brings us to chapter 30. And chapter 30 is about inductance. And so inductance is basically the property of one coil of wire, either with the current running through it, inducing a voltage either in itself or in an adjacent coil of wire or a nearby coil of wire. So we'll start with self-inductance. So you have a current setup with an inductor in it, or a circuit setup with an inductor in it. You turn the power on. The current builds up from 0 to its maximum value, but as the current is building up, the magnetic field inside that coil is changing, or it's increasing, which means the magnetic flux is increasing, which means there's going to be an EMF that opposes the change. And so that EMF is equal to L, which is the self-inductance, multiplied by DI over DT. So it's proportional to the rate of change of current in the wire. And you can also think of the inductance as being equal, comparing that first value to Faraday's law of induction. You can write the inductance as being equal to N, the total number of turns in the coil, times the derivative of the magnetic flux with respect to I, the current. In nearly every case, and certainly in every case that we're going to talk about in introductory physics, the magnetic flux is linearly proportional to the current. So you can simply write that as N times phi b over I. And so ultimately, the I terms are going to cancel out, and phi b is only going to depend on the dimensions of the inductor. Now, the unit of inductance, whether it's self-inductance or mutual inductance, is the Henry. So if the current is changing in amperes per second and the voltage is, or the potential difference is measured in volts, the inductance is going to be measured in Henries. So for a solenoid, a cylindrical coil of wire with N turns, L is equal to N times the magnetic flux divided by I. But the magnetic flux is equal to the magnetic field, and keep in mind that's uniform within a solenoid. So that's N times mu naught N over L times I. And then the area is just the area, the cross-sectional area of a cylinder, which is circular, pi r squared. And you're dividing by I, so the I terms drop out. The N terms multiply together, and what you get is the inductance of a solenoid, or the self-inductance of a solenoid, is equal to mu naught times N squared divided by L times pi r squared. Now, if the coil is a piece of iron inside it, so this gets back to what we've been talking about in a few places, that you put iron inside the solenoid, the rotating electrons with the dipole moments will line up with the magnetic field if you're putting a current through the wire. And so that greatly magnifies the magnetic field. That also greatly magnifies the inductance. So the inductance inside a piece, or inside with a coil of wire with a piece of iron inside it is equal to a constant, a proportionality constant times mu naught times n squared over L times pi r squared. And so that proportionality constant times mu naught is often referred to as mu, or the permeability of iron. And that can be on the order of 2,000. That can be a very large multiplying factor. So that's something to keep in mind. And so we went through a couple of examples with that. Then we talked about mutual inductance. So two nearby coils of wire can influence each other and can induce a potential difference in each other if there's a changing magnetic flux through one. So you have two coils of current I1 and I2, and they have N1 and N2 turns. They're near enough to each other that the respective magnetic fields influence each other. And there are only a couple of cases where you can talk about this simply using mathematics. So for example, you have the two wires wrapped around, you have one coil of wire wrapped around another coil of wire, or interwoven with another coil of wire so that they have the same radius r. Or you can have a coil of wire inside, a small coil of wire inside a wider coil of wire. But there are a limit of examples you can talk about where the mathematics is relatively simple. So we're going to define phy230 as the magnetic flux caused by current 1 on, or caused by coil 1 in coil 2. And phy230 is the magnetic flux caused by coil 2 in coil 1. So we define those, and so the mutual inductance, and keep in mind the mutual inductance is going to be the same regardless of which way you set up the equation. But it's equal to N2 times phy230, so the number of loops in coil 2, multiplied by the magnetic flux that coil 1 exerts on coil 2, divided by I1. And you can also write it as N1, the number of turns in coil 1, multiplied by the magnetic flux that coil 2 exerts on coil 1, divided by I2, the current in coil 2. So those two ways are equivalent. You should get the same answer whichever way you go. And that will be the mutual inductance M, which is also expressed in henries. And the induced voltages are delta V1 is equal to negative N times di2 over dt. And delta V2 is equal to negative N times di1 over dt. And so the change in one influences the other, and that's what mutual inductance is. And the negative sign basically means that you're opposing the change. And so if you have two coils of wire, that one's wrapped around the other, and so you have a clockwise current I1 that's increasing, the induced current in I2 is going to oppose the change, and so you're going to have a counterclockwise current in I2. And but if I1 is clockwise and decreasing, the induced current in I2 is also going to point clockwise. So again, opposing the change. Magnetic fields store energy. Inductors store energy. Capacitors, when they store charge, they're also storing energy. The potential energy stored in an inductor is equal to 1/2 times L, the self-inductance, times I squared. You can write that in terms of the energy density, or the energy stored per volume of the inductor, and that's equal to B squared, so whatever magnetic field is inside the inductor, squared, divided by 2 mu naught. And as it turns out, you can actually store quite a bit, given typical laboratory values for a magnetic field and for an electric field, you can store quite a bit more energy given the space involved in an inductor than you can in a capacitor, enclosing the same amount of volume. And the last thing we talked about is RL circuits. So an RL circuit is a resistor and an inductor in series. the differential equation, so remember for RC circuits, delta V, so the input voltage is equal to the voltage across the capacitor, Q over C, plus the voltage across the resistor, which is R times dQ over dt. So, and we were able to solve that differential equation. And we have a nearly identical, structurally identical equation here. Instead of in terms of charge, it's in terms of the current. So the voltage coming in to the RL circuit, or the RL segment of the circuit, is IR, the voltage across the resistor, plus LDI over dt, which is the voltage across the inductor. And so solving that for I as a function of t, you get delta V over R, which is the maximum current. That's the value of the current you get when at the maximum point, is multiplied by 1 minus e to the negative t over tau. And in this case, the time constant is L divided by R, not L times R, L divided by R. And so that's how you figure out the current. So it's building up to a maximum value, much like the charge in a capacitor builds up to a maximum value. Okay, so that's everything for these chapters. So I wanted to thank you for being part of this course and for putting up with the various quirks and issues with working online. I hope you were able to learn a few things regardless. If you have any questions on the exam or concerning the exam, please let me know. Otherwise, good luck with everything. Have an excellent rest of your summer. Hopefully you get the opportunity to do a few things, and hopefully I'll be able to see some of you in person in the fall. But thank you very much and good luck.